Now we will talk on another actuating device that is widely used in the industry, which is micro valves and micro pumps. So we will just go to the micro valves first and come back to the micro pump. And what you are seeing on the screen is the picture of a micro valve. Now the question is, where do we use this micro valve? Microvalve has got a plenty of application in industry for precise control of gas flow. You need to flow the gas for maybe burning, maybe mixing, in many of the manufacturing process. Similarly, in biomedical applications, you have a lot of requirement of microvalves for controlling the flow of the blood. In the case of a heart surgery, let us say, flow of the blood to the artery. Similarly, you also have a lot of application in pharmaceutical industries where they are used for microfluidic systems. Microfluidic systems is where the fluid has to flow in micrometer tubes with for the purpose of precision analysis for different biomolecule constituents, analysis, separation, sucking, pushing away. So there are plenty of such biomolecule constituents which is in the micrometer level. Therefore, these micro valves plays an important role in such industries, and MEMS microsystem plays an important role. Well, these micro valves again operates on the principle of micro actuation, and here is a design that what you see in front of this figure, where you are going to use the heating of two electrical rings, resistor rings, that is attached to the top of the diaphragm. You can see here this dark one, this dark two things forms the resistor rings, and this is the diaphragm. You can see the diaphragm. Whole thing, you can look at this whole thing, will act like a cantilever, a beam that is extruded from a fixed place. See, there is no fixed place here. So this acts like a cantilever. And what is the use of this is, this cantilever is going to push downwards or come back to its original place. Now when you push downwards and original comebacks, what actually application is going to have is, look at, there is a inlet flow, and there is a path of the flow from here. You can look at this arrow coming from here, going here and coming down, and an outlet flow. So this is a space that is available. Remember, this is a circular shape. What you have to see is, you have to imagine that this is a circular one, and there is a tube, and there is a tube attached here, and there is a diaphragm here. Diaphragm means from here to this edge forms the diaphragm. On top of the diaphragm there is a rings here. So you have to imagine a circular tube, an inlet tube and an outlet tube, and this is a big size tube which controls the flow of inlet to the outlet. Now whenever you apply heat by applying the electricity, this material get hot, then what happens, this beam tends to move downwards, and when it moves towards downwards, look at what happens in this design, that the liquid or the gas is flowing with pressure here. Of course there should be a pressure coming here, coming down here, and it has to pass through this nozzle. It has to pass these outlets. One, it has to pass through this, and it has to come down here. This is the critical point that you have to watch here and see what happens if this entire beam comes down. So what now, you apply the electricity this point, what happens to this beam is, it's going to move towards the downside. Now assume that the liquid is flowing from here to here, and see what happens here. So when application of the heat reduced here, then suddenly the liquid with pressure that is flowing here will be blocked, choked. That means the outlet flow will stop. So this is the idea behind the valve. What is a valve? Valve is something that allows and does not allows. You just imagine your tap. In your tap, let's say you have a head of the tap is a single rectangular head. Then when you turn one side, the water will come. When you turn another side, the water will stop. So this is an application that you require for fluid flow, that is the water flow. Same way, you are applying the pressure through your hand, but there are plenty of applications where you have to apply the pressure through the commands or electric commands. So electric commands is one that is close to the electrical heating rings. That commands will close or open whatever the flow. This will leads into an automatic flow of fluids. Now look at the design part of this diaphragm, which was taken out from some earlier research work, and you have a geometry of this one. You have a diaphragm having the 2.5 mm in diameter. As I told you, this is the silicon diaphragm, which starts from here and ends up to this point. And if you look at this total circular, it is 2.5 mm in diameter. And of course this will be 10 micrometer thickness. If you take from this point to this point, that will give you the thickness, and this will be about 10 micrometer. You can see 2.5 mm and 10 micrometer thickness. So this is then you have a heating rings. These are the heating rings. These heating rings will be of made up of a material, normally aluminum material. This heating ring is made up of a aluminum material, which is 5 micrometer thickness. Then this wall, whatever the wall that is taking, has a capacity of 300 centimeter cube per minute. Okay, so the capacity of this wall to take the volume of the fluid at 300 centimeter cube per minute means you take a block of 300 by 300 by 300 height, that becomes a block of centimeter, and through that you are applying the fluid with some pressure, and the pressure is given is Pascal and PSI. This is not PSI, there is no G here, so it is 100 PSI, and amount of the power that is applied to turn this on or the heat ring on is around 1.5 watts of power. So this gives you an idea that what should be the arrangement that the designer has to do, and normally it's going to operate around 25 psi pressure. So this type of design one has to do in order to achieve the closing and opening of this passage. In turn, you allow the fluid gas to flow or not to flow. Similarly, you also have another design which is another type, where you have a another design with okay, I'll just check this is of the pumps. Okay, I'll just go through the another design that is available in another source. Okay, we'll look at the another design from textbook point of view. Okay, you see here, this is again thermally actuated type of wall, and this is a little bit simpler compared to the previous one. Now the cross section of this type of wall is what you are seeing is a cross section that is it is sliced down from the one point. This design is going to control the flow rate from normally open value wall to a full closed end. So normally it will be open. Whenever you want actuation, it is going to close. Now what happens is, when you heat these rings, which is immersed in the heating liquid, now the whole this part will comes down. When it comes down, it applies the pressure on this this is a membrane, this line, okay, and the whole thing is going to apply the pressure on this diaphragm, what you see here. So the downward bending of the silicone diaphragm what happens is this downward bending of this silicon diaphragm that regulates this inlet and outlet thing. Okay, let's say the fluid or a gas is coming here, it is also filling up it for the proper pressure, and it is going out. Suddenly this will get choked, this area, so it will close down up to here because of the application of the heat through the electric input. Then this closes the outlet, and whenever the heat electrical supply is removed, heat is reduced, then this will again come to the normal position and there will be a flow of heat. So this type of arrangement can also be done where heat source in this case is electrical resistance foils, which is attached to the top of this device. This is one technique in which you can make the micro valves. Of course, all these are in a micrometer and millimeter dimensions, which is mostly applicable in micro systems or very small application where you can't put your hand pressure, you can't put your external force physically. You want the electronic circuits or the intelligent smart circuits to take decision. You can use in that type of application. Next, what we do is we go into the micro pumps. Again, micro pump, you know what is the use of a pump. Most of you at home, you may be having a pump. What does a pump is going to do? A pump is going to suck somewhere, and it is going to put that whatever it has sucked into another point. Just imagine your water pump where it takes the water from your sump tank, from where it is going to suck the water. After sucking, what are you going to do? You are going to push that into some other point, probably in an overheated tank, and you are going to push there, pull it and push it there. These type of plenty of requirements are there in the industry where you need to suck the fluid or a gas, and you have to release that into another point, but you have to do all with this pressure. So pressure, creating the pressure, sucking and exiting, all these things are a requirement in plenty of applications. That too also required in micrometer level. So you also going to use this simple micro pump where you can use a electrostatic actuation. Probably you are familiar with capacitor, that what we discussed for producing the electrostatic actuation. Again, we are going to recall that here. So again you are having a deformable silicon diaphragm that forms one electrode of the capacitor. So you can see deformable is the bottom thick line. Okay, this forms the black line from here going here and here, to which is this part of the voltmeter is connected. This is the deformable part of this capacitor. Another plate of the capacitor is this, which is connected to here. So this is a capacitor arrangement, and we are going to produce electrostatic force by applying the voltage or an EMF. Now whenever the deformation takes place in this part of the plate, that is the actuation that is going to take place, followed by this pumping chamber. So we will see this pumping chamber part, what happens if a deformation takes place due to the actuation. Now now let us imagine that this diaphragm, when you apply a voltage, it moves upwards. Okay, so you will have an upward motion of the diaphragm. What will happen to the upward motion of the diaphragm? This will increase the volume of the pumping chamber. Now you see, this is the pumping chamber, a chamber in which you will have the liquid, where the liquid is entered through the inlet. Let us see how this operates later on. Let us say this is the inlet from where very low pressure normal fluid will be flowing here, but that will get accumulated in this chamber. Why do you need a chamber? We need a chamber to create pressure for the exit of the fluid. But the inlet need not be a high pressure one, but chamber volume, and decreasing and increasing the volume of the chamber creates the pressure. So pumping action is there. Therefore, the inlet is going to be coming from this direction, and it is going to fill the pumping chamber. When it is going to fill, you watch what happens now. When you apply the electric potential, you assume that this electrode deforms and go upwards, when you go upwards, this is assume that this is a flexible chamber. You have a silicon material that are flexible. Okay. So look at this check wall. This check wall, you have to imagine this like a cantilever beam that is placed on the top of this area. This point is very critical, this particular point. Okay, and so that is critical. So this wall is going to go upwards. Why it is going upwards? Because this is going upwards. When the pressure is decreasing, this is going to open. What happens when this is opens here? The low pressure inlet fluid simply fills the chamber. So this happens whenever you apply the potential and when there is an upward movement of the silicon or this electrode that has taken place. So there will be a reduction in the pressure which causes the inlet check wall to open, and this allows the inflow of the fluid. Now suddenly if you take out this applied voltage cut off, you say cutting off the voltage to the electrodes, this will make the diaphragm to return to its initial position. So this will going up and it will come back to initial position. This causes the reduction of the volume. So the reduction of pressure that causes the inlet check to open, and it allows the inlet flow. Now subsequently removing of the applied voltage to the electrode prompts the diaphragm to return to its original or initial position. So this going back will cause the reduction in the volume of the pump chamber. So this is the pump chamber, and this makes the reduction, and this volume will get reduced. Okay, the volume that was higher because of the upward movement, now when it comes back to the original position and liquid is also there and this has been closed, now the total volume that was compared to the when it was opened got reduced. Now reduction in the volume performs what? Increase in the pressure of the entrapped fluid in the chamber. So this pressure will get increased because the volume has decreased. This causes the outlet check valve to open, and fluid pressure reaches that particular pressure and the fluid will release. So you can see here this part of this check valve. This check valve will go into, this is like a beam, this comes down due to the pressure and this will come out and it will be going out. So this is a pumping action that you can see, and there are plenty of such devices. This pump is designed with a diaphragm of 4 mm by 4 mm by 25 mm thickness. So this is the diaphragm and that is the thickness. Then the gap between this diaphragm will be around 4 micrometer. This gap that exists between these two will be around 4 mm. Then the frequency at which this operates, on off frequency, will be about 100 Hz. And at 25 Hz, if you calculate, suppose when the operating at 25 Hz for the purpose of calculation, then the pumping will be doing about 70 microliter is achieved per minute. Okay, 1 minute there will be 70 microliter fluid will be coming and going out. So this is one type of micro pumps that you can see sucking and releasing action is achieved due to the electrostatic actuation. Similarly, you also have another type of micro pump which you call it as a piezo pump. This piezo pump is again works on the producing the wave type of motion in the flexible wall in which fluid will flow. So this will also look like this. You see this piezoelectrically actuated pump, which will look like this, where piezoelectric crystals is coated on outside of the tube wall in order to produce the wave shape of the heating. So this is the piezoelectric coating which is coated on outside. You have to imagine this like a tube. This is the outlet of a tube, and backside you have an inlet, or it can be flow can be taking place in this direction, the flow. This is the point of the flow, or you can take the direction of the flow. It is just like a tube. You can consider this like a tube, where this is the inlet and this is the outlet, and this is the flexible one, which whenever the pressure is applied, this like silicone material or plastic material which gets deformed or flexible. So these piezoelectric materials which is coated outside the tube will generate the wave type of the motion. You know, the wave type of the motion is coming down, going up. Whenever both will come down, what happens? Squeezing takes place. Okay, you know, when you apply the pressure on a tube, when you apply the pressure, something will come out. When you remove, like your toothpaste tube, when you remove the pressure on the toothpaste tube, the material inside will not come out. So something like wave type of the motion can be exerted on this tube, and you can also achieve the pumping action. But what you used to do for your toothpaste tube, you can also do it not through your hand but through the electrical application on the piezoresistors. So this gives you an idea about a pumping action that can be achieved. Okay, so we'll stop here and continue with the micro accelerometers later on.